I work at the SMHI, Swedish Meteorological and Hydrological Institute, at the research department, the meteorological unit. Today, I will give a short overview of the Swedish weather radar network. I will also give you 2 challenges we currently have or recently resolved. So let's start with an overview of the whole network. So the Swedish weather radar network consists of 12 C-band dual-pole Doppler weather radars from EEC. They have a nominal peak power of 250 kilowatt, powered by magnetron. So between 2014 and 2021, the whole network was modernized from old Ericsson single-pole Doppler systems. The network is jointly managed by the SMHI and the Swedish Armed Forces. As of the modernization, all 12 radars are owned by SMHI. Previously, they were owned both by SMHI and the Swedish Armed Forces. Maintenance of the network has always been contracted to an external party. The current maintenance provider is Combitech. That is an independent company and a part of the defense and security group, Saab. The figure here illustrates the coverage of the radar network as height above ground level of the lowest operational elevation angle of 0.5 degrees. So let's move on to an ongoing challenge. During the modernization, or actually prior to that, the contractor decided to retain the old transmitter units that was manufactured by Pulse Systems. During the final phase of the modernization, the radars were consistently calibrated and configured to produce good quality data for dual-pole applications. So since November 2020, all our radars performed in star mode, that is simultaneous transmit and receive. But however, the magnetrons started to fail way ahead of their expected lifespan. The first system started to experience problem just after about 6 months in this new operation. I'm unsure how old that specific magnetron was at that time. Anyway, the small inventory of magnetrons was soon exhausted, and for that time being, we also had long delivery times of new magnetrons. So that forces to degrade all our radars to single pole. This photo here, it depicts an old worn out magnetron from CPI. So the root cause. We found out that the transmitter were actually running the magnetrons out of specification. The probable cause of failure was excessive heating of the filament during operation. So constant heater power and back bombardment from running it. So running the long pulse width and the high duty cycle, as far as I understand, leads to instabilities such as arcing, which in turn leads into a shortened lifespan of the magnetron due to depletion of emissive material of the filament. So what we had to do was to shorten the pulse width and also lower the duty cycle. So the consequences of this led us to reduce sensitivity and reduce range for dual pole applications. So since June this year, all our radars are actually running now on single pole H mode only. So the short-term solution, as I said, was to degrade the radar to single pole. But our medium-term solution is actually to try to increase the duty cycle of the magnetron using our current transmitters. And well, of course, the long-term solution would be to purchase new transmitters. But move back to the medium-term solution. So in order to increase the duty cycle of our magnetrons to make full use of dual pole capacity, and also keep magnetrons within the tolerances, we need to modify our current transmitter unit. So the proposed solution is actually to regulate the heater voltage automatically with respect to current operating condition. So the regulator needs input on a pulse repetition frequency and the pulse width, and the output will be the heater voltage. I believe a modern transmitter unit includes feature to regulate this heater power. Our old one doesn't. So our maintenance provider will start soon, hopefully at the beginning of next year, to develop this kind of regulator. And if it's successful, we hope we will have it equipped. We'll have it installed and to equip all our systems within a year. So let's move on to another recently resolved challenge. So radar ATV is located some 180 kilometers southwest of Stockholm. Back in 2019, just a few months after the modernization of the radar, we observed that the intensity varied on a regular basis. And this was clearly seen in the composite during stratiform events. So here's an example sequence. It's 1 full hour of 0.5 degree sweeps. Quantity is TH, the total reflectivity. So that's why you have a lot of clutter going on, but it's clearly seen that it pulsates regularly. So the interval between two frames in this animation is about 5 minutes. In order to assess this, we started to look at the data quite closely. Here is a distribution of 2 consecutive 0.5 degree elevation sweep. In this case, where this quantity is filtered intensity. But as you can see, it shifts both towards higher intensity, and also the number doesn't really add up. So, so we started to look at this more closely. So by flipping the orientation of these distributions to vertical and coloring them with respect to the number of hits given by each event, each 5-minute sweep, we could see a pattern emerge quite clearly. So in this middle image, you can see the intensity on the vertical axis and the time on the horizontal axis. And the time span of this image is about 8 hours. So one thing we did was to change the schedule, try to manipulate what schedule or what the radar or actually the antenna was doing immediately before start of every operational volume. So what we see here in this image is basically the same thing as in the middle image, but we do some changes to the schedule. The time span of this is a bit shorter, it's about 5 hours. So between every 2 operational volume of 10 sweep, this schedule includes some auxiliary sweeps for evaluation, both calibration, also idling, waiting for the next sweep to start. We could also see this pulsating behavior at 1 degree elevation angle as well. That is the subsequent to the 0.5 in our scanning scheme. We spent actually countless hours to find the root cause of this issue. Here is just a timeline of the major events we have done and experienced. So, as I said, back in 2019, we first observed this behavior. Initially, the gearbox was assessed as okay, the gearbox for elevation drive. Instead, focus shifted towards any component that could contribute or explain this kind of behavior. So most of the components in the radar cabinet was replaced, except for the transmitter unit. We investigated the structural integrity of the just on the 20-meter high truss tower. That's the tower that supports the platform where the pedestal and antenna is located. They found a couple of loose diagonals in the truss tower due to loose bolts. So to be on the safe side, we had all the bolts replaced one by one. And to prevent the bolt from coming loose, this time the threads were deformed between the nut and the bolt, trying to prevent the nut from unscrewing itself. So apparently, as I understand it, the tower was assembled with some kind of self-locking nut. I don't know which one. We also had inclinometers installed to independently measure the antenna movement and the pedestal movement. And our results only concluded that the tower was stationary and could not explain the varying intensity. The receiver was checked during operations by injecting a known signal from the system's built-in test signal generator. Finally, we also replaced the transmitter and magnetron. But eventually, the root cause was found. There was a play in the elevation gearbox, and a gearbox replacement was performed, and the problem was fixed. So, simple is better, right? After we exhausted all possible causes, we returned to the mechanics to have a closer look into what's going on. So we wanted to know whether the antenna was consistently returning to the same position. So the field engineers invented a method using just an ordinary laser pointer and a marker pen. And well, they mounted they attached the laser pointer onto the counterweights, as you can see here on the left-hand side image. And I also put a marker on the inside of the wall of the radome. So what you see here on the right-hand side is, well, I believe is the starting point, marked in as a blue dot, and the current position marked from the laser pointer. The duct tape here is about 5 centimeters wide. So, well, as I also learned, the total deviation is a bit wider than the tape itself. So this is only a fraction of the total movement, or how the antenna settles each time varies more than the width of this tape, as seen in this image. So moving back a bit, the contractor of the modernization decided to retain the elevation gearbox from the old systems. The gearbox itself has a kind of ball screw inside that handled movement, and a visual inspection and some elbow grease clearly indicated radial and tangential play of the ball screw shaft. As the ball screw shaft is seen in the image here. On the left-hand side, it has a crank attached to it. So in May this year, the gearbox was replaced, and this fixed the problem. And any remaining intensity variation is hardly discernible. We also tried to provoke all other systems in the network to see if they have a similar issue, but no one exhibited the same behavior, at least not at this magnitude. Photos from the last two slides are from Combitech during their investigation and work on this. So the take-home message of all this is analyze your data, assume nothing, and keep it simple. So if you have any questions, don't hesitate to contact me or my colleagues. I also want to acknowledge my colleagues at SMHI and our external party Combitech for their contributions to make this presentation possible. Also, the radar seen in this photo is actually radar Kiruna during its modernization in 2021. It was the last radar to be modernized, and yeah, it's a special place, middle of nowhere, basically, roadless, wireless. And also, one more thing. If you have or know someone that has or knew or used transmitter pods, especially this pulse system, high voltage power supply, and pulse systems modulator, please contact us. Thank you.
Thank you very much.
This is Mikko Kuri, SMHI. Did you ever check the solar monitoring results? Or did you see there anything? Because in the solar week, for example, it could have been seen. I don't know. Did you check?
I did not hear the full question. Could you please repeat that?
Can you hear me now?
Yes.
Oh, okay, yes. I was asking about the solar monitoring.
Yeah,
did you check the antenna pointing based on solar monitoring or the solar width?
Yes, we did. We didn't find any evidence of anything, probably because the deviation was only affecting lowest elevation angles, and I believe it was smeared out or averaged out from all other observations of the sun. So we couldn't really see if that this radar was worse or experienced some deviation compared to others.